everyone, my name is Wen Zhang. I'm from the University of Manchester. So today I'm going to talk about the effect of anisotropic microstructure on the fatigue overload behavior of ultrafine grain nickel. So what is fatigue overload? Fatigue overload is a transient increase in the external load, seen here. So Pmax and Pmin are the maximum load and the minimum load for baseline fatigue. And so we know that the fatigue crack growth rate is a function of the stress range and the mean stress. So this is a characteristic crack growth rate after overload. We can say this decrease in the crack growth rate. So what are the mechanisms for that? Residual stress is one of the main mechanisms for this. So we can say this is the overload plastic zone. So and the rest is the material in the elastic regime. So what's the difference between elasticity and plasticity? So let's take the spring as an example. So when a moderate load is applied on the spring after it is removed, the deformation can be fully recovered. However, for plasticity, if we apply a large load, when the load is removed, only part of the deformation can be recovered. So, during unloading, the elastic recovery will compress this region. So a compressive stress zone is generated within this overload plastic zone. So the residual stress can lower the whole stress, we can say here, and then if the residual stress is too significant, it can give rise to closure. So another mechanism is plasticity-induced crack closure. This is the SEM image after the whole experiment showing that crack face contact occurs over a distance immediately after the crack tip that holds the rest of the crack open. So this will reduce this premature crack face contact will reduce the stress range and therefore retard the crack growth. So there are some other secondary mechanisms. They can either reduce the stress range or the mean stress or both. So traditionally for the coarse grain sample, the retardation mechanisms are well understood. But for ultrafine grain material, because of the grain refinement can lead to higher yield stress at the then smaller plastic zone. So we wonder, can overload retard the fatigue crack growth rate? And if so, what are the retardation mechanisms? So this is a material used for the experiment. The ultrafine material is produced by the high pressure torsion technique. So the coarse grain material is placed in between the anvils, the two anvils, and the pressure, and with a shear strain can be generated with the rotation of the lower anvil, so that we can get the ultrafine grain disc, and then the two compact tension samples can be extracted in two different directions. And here is the radiograph collected at synchrotron. So we can say after the experiment, we can say that the cracks for both cases are not straight, they are deflected. So why is that? Then we did EBSD. So we observed that the grain elongation for both cases. So the crack for both cases tends to propagate along the elongation direction. So does that, this anisotropic microstructure, have an effect on the fatigue overload behavior? This is the experiment I did in a synchrotron facility in the UK. So here is the fatigue rig. It's mounted on the sample table, and this is the sample. And the DIC camera is mounted on the step motor that can be moved in to measure the crack length, and do the image correlation, and then can be moved out for X-ray measurements. The diffraction signals can be collected by the diffraction detector, and the radiographs can be collected by the image camera. So this is the in situ experiment, and this enables the DIC and X-ray diffraction measurement at the same loading levels. So this is the details for the experiment. This video is taken by DIC camera. We can say before overload, at overload, and after overload. So this is the result. This is the fatigue crack growth result. So we can say for both cases, the crack growth rates are retarded, however, to different degrees. For the TR sample here, the crack growth rate is more retarded. So the following results are going to explain why is that. So we did this is the synchrotron X-ray diffraction results. It's the stress field around the crack tip in the crack opening direction at the maximum load. Here we can say overload minus 1. This means one cycle before overload. And we can say the crack, the stress is increased by the overload event. And after overload, we can say one thousand cycle after overload, we can say the stress for both cases are reduced, however, to different levels. So for TR case, this is more significantly reduced due to the residual stress effect. And then after the crack has propagated out of the plastic zone here, we can say the stress is recovered to the baseline state. So we also did the map scan for at minimum load. So we can observe the same trend at that maximum load. So the advantage for this is we can directly measure the residual stress after overload. We can say for both cases the stress at P min is reduced, and for different levels. Of course, for TR case, a more significant residual stress is observed here, and then recover to the baseline state. So we observe the decrease in the stress, but if we want to know how much exactly the stress is reduced, or the stress intensity factor is reduced, we can do the fitting. So I use Williams' approach to fit the strain field in the crack opening direction. So we can get the effective Kmax and Kmin, and therefore we can get the effective stress intensity factor range. This is the results, fitting results at Pmax. We can say that for TR, the stress intensity factor is more significantly reduced. So we also did DIC. This is DIC results. From the DIC displacement field, we can get a lot of information. So for example, the crack opening displacement, the J integral, and the K. So this is the crack opening displacement as a function of the distance from the crack tip. 0 is the crack tip. So we can observe after overload, we can observe the crack face contact here. So this is verifies that the crack closure occurs. However, for TR sample, for this sample, the crack closure effect, plasticity induced crack closure effect is more significant. Also, similarly, we can also fit the displacement field and with Williams approach, and we can observe this is the result, and we can observe that this is stress intensity factor range for TR cases more reduced. So we also did fractography after the fractography analysis after the experiment. For the TR case, we can observe this overload boundary and the flat and dark regions showing the characteristic closure scars. However, for this TR sample, we can also observe crack face contact, but to a smaller level. So roughness can be a very important factor that can induce crack closure. So we did a 3D roughness measurement, showing that for TR case, the roughness is higher than the 80. So this is the conclusion. So fatigue overload retardation is observed for both samples, but for the for TR cases more retarded because of the more significant plasticity-induced crack closure compared with residual stress and crack deflection and roughness